Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today we're going to talk about a subject that I've always found fascinating, and that is radiometric dating. How do we tell how old a rock or a piece of pottery is? Now, this involves the use of radioactive isotopes. Now, one such radioisotope is something called carbon 14. Now, in our atmosphere, we have a gas called carbon dioxide. Now, the reason that we like to use carbon dioxide is it's ubiquitous in our atmosphere and it's got a relatively stable level. Now, normal carbon is carbon 12, but it also has a radioisotope called carbon 14 that is formed in the upper atmosphere due to interaction with cosmic rays. So a tiny percentage of the CO2 in our atmosphere will have carbon 14 radioisotopes. And as a result of that, as that carbon dioxide is incorporated into our bodies or into the substance of a tree or something or other like that, there's a certain amount of carbon 14 present in all living organisms. When those organisms die, that carbon 14 is no longer being replenished, and it begins to age out or go through a decay. So say you have a living tree. If you analyze the wood in that tree, there will be a certain amount of carbon 14 present. When that tree dies, it's no longer interacting with the environment, and the percentage of carbon 14 in that wood will begin to decrease. And that brings up the concept of something called a half-life. Now, for example, the half-life of carbon 14 is 5,730 years. And what that means is if you have a piece of wood, if it's a brand new piece of wood, you'll have 100% of the carbon 14 that would be expected to be in that wood. Now, after 5,730 years, you'll only have 50%. Now, if you go another 5,730 years, you will lose half of what is left. So in other words, you'll go down to 25% at the end of 2 half-lives, 12.5% at the end of 3. So let's cue up the music and find out how we use radiometric dating to find the age of objects. And then we'll take a second part, kind of a bonus feature, and we'll see how the science-denying community tries to misuse radiometric dating to promote their narrative. So let's go. Okay, so here's the basic principle behind it. At time 0, we have 100% of the carbon 14 in our sample. At 5,730 years, we're going to have 50%. Now that only leaves 50% to work with. So if we go another 5,730 years, we'll be down to 25%. We do another half-life, 5,730 years, we're at 12.5, and so on and so on and so on. Now, a key to understanding how this is useful to us is to have a look at the number of half-lives that we can use. Now, if we look at this first half-life, we're going to have a drop in the amount of carbon 14 by 50%. However, there's going to be a limit to what we can actually detect. So this particular area right here, for example, we may not be able to adequately measure. So the earliest that we could date something would start about right there, which will be sometime after 0. Now we can also go out here to about 10 half-lives. And after that, we have so little left, it's essentially 0%, and we can't really adequately measure it. So carbon 14 dating is good from probably 2,000 years to about 60,000 years. If our sample is younger than 2,000 years, carbon 14 is not the tool to use. If the sample does not have carbon in it, carbon 14 dating won't help us very much. And if the sample is older than about 60,000 years, again, we need another technique. Now, a couple of quick notes about carbon 14 dating and radiometric dating in general. Radiometric dating generally does not stand on its own. So we look at radiometric dating as one of a number of tools that we use to try and figure out how old something is. Radiometric dating is one. The layer of rock that it is found in is another one. Historical records may be used as well. So if we look at an event such as the eruption of Mount Vesuvius and the destruction of Pompeii and Herculaneum in 79 AD, we have a rough idea of the age of the artifacts that are in that area. Now, at slightly over 2,000 years ago, radiometric dating with carbon-14 would be a little bit iffy because that's right at the limit of what it can do. However, there are other techniques that we can use that have a shorter half-life to date that material to within a decade or two. And that can be used, for example, as a test of the accuracy of the dating technique. Now, the mathematics behind doing radiometric dating can be rather complex, but what I'm going to do today is I'm going to show you a very simple way of doing it with a slide rule, which is how the technique was developed in the first place. And to do that, we're going to use something called the log-log scales. So let's go ahead and have a look at the slide rule. Now, to give you an idea of what we're using a Faber-Castell 283. This is considered by many to be the most accurate and beautiful slide rule ever made. It was developed in 1975 at the very end of the slide rule era, and I purchased this from a collector in Turkey. It has our standard scales, the C and D, the A and the B, the folded scales, the inverted scales, etc. However, on the other side, we have something called the log-log scales. Now, to figure out a half-life, what we need to do is we need to come up to the 0.5 mark on our LL2 scale in red, and you can see that right here. See? That's 0.05. Now, underneath that, what we're going to do is we're going to put 573, which is going to be about right there. Now, for some slide rules, for example, on this picket, we kind of luck out with something, and that is to convert degrees to radians, you divide the number of degrees by 57.3, and as a result, there is a small mark right on the slide rule at 57.3. Now, by sheer chance, this also corresponds to the half-life of carbon-14, so if you happen to have this mark on your slide rule, that just makes it a little easier. But we don't like to make things easier, so we're going to do it by hand right now. We're on 0.5 here, and then on the sliding C scale, which is right here, we're going to go, that's 55, 56, 57, and about 57.3 right there. Now we have our slide rule set up as a table. We don't have to do anything else to it. Say we have a piece of wood, and it has 1.5% of the carbon-14 remaining. So how old would that piece of wood be? Well, at the end of one half-life, the object would be 5,730 years old. At the end of two half-lives, we would find the 25% mark, which is right here, and then we'd simply read down onto the C scale and see what we had. So this would be 10,000, 11,000, 11,470. So let's go check that real quick with the calculator just to make sure that we understand it. And there's our answer, 11,460. And if you look right here, that's pretty much what we had. I said 11,470 just eyeballing it. But if you wanted to get a little bit closer, you could. So that's at 25%, but we don't have 25%. What we have is 1.5%. 1.5%, 1% would be 10 to the negative 2, which is right here. 2% would be right next to it at 0.02, and 1.5% would be right in the middle. Now we read down to our C scale, and we see 3, 4, 6. All right, so where do we put our decimal place? Now, if we were on the same scale as our 0.5 right here, say we were here at 0.65, well, we just read right down, and our answer would be here at about 36. Well, this will be the same order of magnitude as our 0.5 because it's on the same scale. So that would be 3,600 years. And that makes sense because if we have 65% of our carbon-14 activity, we haven't quite made it to one half-life yet, which would be 50%. However, if we're on the scale above it, we have to multiply our answer on the C scale by 10, because that's a factor of 10 greater. So if we actually read our number right here, we're going to have 34.6. Instead of being 3,460 years, that would be 34,600 years. Say we have 10% left. Well, we can go ahead and find that as well. So once again, we start off at 50 and 5,730 years. And now we look for the 10% mark. 10% is going to be right up here. So we know that 10% is going to be considerably less than 50%, and it's considerably more than 1.5%. So that kind of gives us a range of where our number is going to end up being. And if we look right down below here onto the C scale, we'll see we've got about 19. Now, what is that 19? Well, it's not 1900, it's 19,000 years. Now, while this is pretty easy to do with a slide rule, what if you don't have a slide rule? What fun would there be if we didn't know some math? Let's learn a little bit about logarithms. Say we have two numbers, x and y. Log x plus log y equals log x times y. Log x minus log y equals log x divided by y. And if you have log x raised to the power of y, that equals y times log x. So in other words, you can take that exponent and just bring it right around to the front. The log of 1 is 0 because x raised to the power of 0 equals 1, and that works for any x. Now when we talk about log, we're talking about log base 10. That's called common log. If we talk about the natural logarithm, that's log to the base e. We'll talk about what e is another time. Now the last thing that we need to know is that if we have log base x of x, that always equals 1. So if we have the natural log of e, that will equal 1. The log of 10 would equal 1. Now here's the basic formula for figuring out radiometric dating. Given a certain amount of time, that means that e raised to the power of negative t times a constant will equal the percentage of the original carbon-14 in the sample. Now you can use any radiometric isotope in place of this carbon-14, but we'll use carbon-14 as the example. So the half-life of carbon-14 is 5,730 years. And that will equal e raised to the negative 5,730 times this constant c, and that will equal 0.5 of the original carbon-14, or 50%. Now the half-life of carbon-14 is 5,730 years, and that's the time it takes for half of the carbon-14 in the sample to go away. Now let's look at this equation right here, because this is a little less complicated than you would think it would be. Notice that we have e here. Recall that if we take the natural logarithm of e raised to the negative 5,730 times c equals the natural logarithm of 1/2, which is what 0.5 is, we can actually solve for some of these things and figure out some stuff. Recall that if we're taking the log of a number that's raised to an exponent, we can bring that exponent around to the front. So now we have negative 5,730c times the natural logarithm of e equals the natural logarithm of 1/2. Recall that the log of a number taken to the log of that same number equals 1. We can rewrite this as negative 573c times 1 equals the natural log of 1/2. Now we can make one more change to this. So we've got negative 5730c equals the natural log of 1 minus the natural log of 2. Because when we have 1 over 2, we can take the log of 1 minus the log of 2 and find the log of 1 over 2. Now, this number right here equals 0. So, negative 5730c equals negative natural log of 2. So we're in pretty good shape right now. Now to solve for c, what we have to do is we have to take negative 5730 and divide that into a natural log of 2. So c equals negative natural log of 2 over negative 5730. Okay, we're going to go ahead and do a quick problem here just to show. Say that we have a sample that has 10% of the original C14 in it. And we want to know how old that is. So we're going to convert this around a little bit. We're going to say it has 1/10 of the original C14. That'll make things a little bit easier here in a moment. So for carbon-14, our constant is the natural log of 2 over 5,730, which is the half-life of carbon-14. Now, recall that our original equation is e raised to the power of negative t times c equals 1/10, because we have 1/10 of the original carbon-14 left. What we want to do is we want to solve here for t. So we'll take the natural log of e raised to the power of negative tc equals the natural log of 1/10. The natural log of e is 1, and we can bring the exponent down, so we get negative tc equals the natural log of 1 over 10. Recall the natural log of 1 over 10 is the natural log of 1 minus the natural log of 10. This equals 0. So our answer is the negative natural log of 10. So negative tc equals negative natural log of 10. Now we can divide both sides by negative c, and we get t equals negative natural log of 10 over negative c. Now these negatives, of course, will cancel. This ends up being natural log of 10 over natural log of 2 times 5,730. Here we had natural log of 2 over 5,730. Here we've inverted it because we're dividing by c. Now it's 5,730 over natural log of 2. Hopefully that'll make some sense. So what we'll do here is we will take 10 natural log divided by 2 natural log equals. Then we'll multiply it times 5,730, and that gives us an answer of 19,034 years. Now 19,000 is close enough because it's not exact. Now if we go back to our slide rule, we have it all set up here with, here's the 0.5, and here's 5,730 on the C scale down here. So here we are at 10%, 0.1, and we read straight down, and we are just a hair over 19,000. There's 18, there's 20, there's 19 right underneath the cursor. And as you can tell, we're right on the money there. So there we did it two different ways. We used a slide rule and we used the actual formula with a calculator. The slide rule I find a little bit easier and quicker, but you can use a calculator if you wish. Now it's absolutely key to use the correct radiometric dating method when you're looking at a sample. For example, if you're dealing with something that's out to about 60,000 years old that has organic carbon in it, carbon-14 works very well. That's because carbon-14 has a half-life of 5,730 years. Now, if you're dealing with a rock that's 1 billion years old, that carbon-14 dating is not going to help you. Potassium argon very well may, because it's got a half-life of 1.2 billion years. But however, it won't be able to give you an accurate reading on a sample that's less than, say, 1,000,000 years old. Which is why recently, when some science denial groups came out and tried to pull a fast one to discredit radiometric dating, they took a rock that had a known age of 35 years. They misrepresented the age of the rock and took it to a lab and requested specifically the potassium-argon dating be done, with a half-life of 1.2 billion years. As a result, when the results came back of somewhere between 250 and 1,000,000 years, they were able to flaunt the idea that, well, this rock's 35 years old, but it came back as being 250,000 years old. You see how they manipulated the system? You need to be aware of that type of manipulation by groups that have a narrative. They make unreasonable demands of the system. That's an example of an unreasonable demand, using the wrong radiometric method to date a very young rock of known age. The other thing that they'll do is they'll demand that, well, if you weren't there to measure the original amount of carbon-14 in a sample, you can't estimate what that is. Again, not true, but it's an artificial demand being put on science to try and discredit the truth in favor of their narrative. Likewise, they try and raise questions about, well, how do we know the radiometric decay rate was stable throughout this period of time? Well, that may be valid if you're talking about one particular radioisotope, and that being the only way that we date things. First of all, we have a number of different radioisotopes, and the idea that every single one of them is flawed in exactly the same way, despite the fact they have various half-lives, is just ludicrous. Plus, as I said, we have reference material of known age. We also take into account other clues as to the dates, such as the strata of rock, or a relationship to a known event. So when you hear claims that radiometric dating is not accurate, take that with a little grain of salt. Now, we'll have an episode on conspiratorial thinking, young Earth creationists, etc., and their attempts to overturn radiometric dating in another episode. In the meantime, let's stick with the science on this one. So, this is Bob the Science Guy signing out from Northern Michigan. Thank you again for stopping by. Make sure you hit that like and subscribe. I'd love to have you as a member or a Patreon of this channel, and we'll continue to do good work here. Take care, guys.
Mama, please make them hear me. I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.